So in this question, we are asked to prove that the Hilbert space and its dual space isometrically isomorphic. This symbol means isometrically isomorphic. So in this question, there are so many things to do in order to prove that these two spaces are isometrically isomorphic. First of all, we will look into the notations and terms. What does this exactly means? So first of all, what is the dual space? Dual space is the set of all bounded linear functionals from considering set to underlying scalar field. This field could be reals or complex numbers. So these are set of functions or other functionals which is bounded and linear. So if we form a set of all bounded and linear functionals, we get this dual space of X. Okay, so then we have some terms to introduce here. Uh, so in a Hilbert space, Hilbert space, so in a Hilbert space, the set of all bounded and linear functionals looks like this. It has the form of this. So here LG means a function from dual space to underline scalar field, which gives it takes each h in capital H, which means each h in Hilbert space, and it converted that vector into an inner product with some other vector g. So basically, these all functions L of g LGs are depends on the uh, vector g we take in order to calculate the function. So here, what here's the equation of the function. What exactly the function does to this h? It takes h and take the inner product of considering with the inner product of considering the vector g. Then we have a real number. We have a real number. Okay. So we can prove that this function is bounded and linear. So uh, we take this property of the dual space of Hilbert space in order to prove these two spaces are isometrically isomorphic. So in order to prove that, we need a theorem called Riez representation theorem. So what does that mean? So basically, this function says for each g in H, which means each vector in the Hilbert space, we have a bounded linear functional in the dual space of H, which means each vector in the Hilbert space H, we have a bounded linear functional along its dual space. Riez representation theorem guarantees the converse is true, which means if we pick a bounded linear functional in dual space, we can find a unique vector in Hilbert space that attached to it's kind of a attachment of this attachment to the bounded linear functional in the dual space. So Riez representation and together with this property of Hilbert spaces gives us the one-to-one correspondence between Hilbert space and its dual space. So Riez representation theorem guarantees the converse of this property. This property guarantees that each vector G in Hilbert space has a bounded linear functional in its dual space. So together with these two properties, we can form a one-to-one correspondence between Hilbert space and its dual space. Okay, so isometrically isomorphic. So what does what do we have to prove? These two spaces are isometrically isomorphic. Isometrically isomorphic means they exist bijective bijective there exists a functional which is bijective, isometry, and linear. So we have to find a function which is h to its dual space h star which is bijective, linear, and isometry. So here isometry is a function which preserves the distance. I will talk about that in a bit. Okay, so answer is here. First of all, we define a function from h to h star, which means we define a function or rather operator t, sorry, other rather function t, Hilbert space to its dual space, which has this form. T of g is equal to LG. LG means these functions. Okay, so this is a well-defined map clearly. So now we have to prove that T is linear. First of all, the now three conditions should satisfy. T should be linear, bijective, and isometry in order to prove that H and H star has the same structure. Rather, it's isometrically isomorphic. So we pick any generic two vectors in Hilbert space G1 and G2 and the alpha 1 and alpha 2 in underlying vector field R. Here this could be a complex number field as well, but in order to be H and H star, in order to be isometrically isomorphic, underlying scalar field should be real numbers. I will tell you why in the proof of when we show in the linear part, which is this part. So we pick these four these two scalars and these two vectors. Then we evaluate alpha 1 g1 plus alpha 2 g2. So we get this one. By the definition, we get the inner product of this one. So by the properties of inner product, we can separate these two terms, which we get the inner product between h and alpha 1 g1 plus the inner product with h with inner product h with alpha 2 g2. So by the properties of inner product, again, we can factor out the scalar by taking complex conjugate of this one. But these are real numbers. So alpha 1 bar and alpha 1 is equal. Alpha 2 bar and alpha 2 is equal. So again, by the definition, this is LG1 and LG2, which is alpha 1 TG1, alpha 2 TG2, which is clearly this result shows clearly we can conclude T is linear. Okay. Now we have to prove T is bijective, which means we have to prove T is 1 to 1 and T is on 2. In order to prove T is 1 to 1, we pick two generic vectors in the Hilbert space H and we take the equality of these two outputs, T of G1 and T of G2. We must show that G1 and G2 equals. So by the definition, again, this is L of G1 and this is L of G2. Then again, by the definition, this is the inner product of H and G1. This is the inner product of H with G2. Again, if we use the properties of inner product, we get this one. This simply means the inner product is 0, which guarantees this H is orthogonal to this G1 minus G2. Recall the dot product is 0 when those two vectors are perpendicular, right? So the same generalization of dot product is the inner product. So same thing applies here, and we get H is H is perpendicular to this vector, which guarantees G1 and G2 in the perp of H, which means H perp. H perp means orthogonal complement of H. Orthogonal complement means the set of all vectors which is perpendicular to considering set. Now here H perp means set of all vectors which is perpendicular to all vectors in the Hilbert space, which is we can prove that this is only 0 vector is the perpendicular to all the vectors in Hilbert space. So G1 and G2 must equal to 0. Then we can imply G1 equal to G2. So that is the one-to-one part. Here on to part directly comes from the Riez representation theorem. So we pick any bounded linear functional in H star, and we have to show that there exists a unique G in Hilbert space, or the domain of the function, domain of the function T, such that uh, this G should exist. So by the Riez representation theorem guarantees such G exists. So T is clearly onto. Thus we conclude T is bijective. So this is the isometry. Isometry means basically the distance preserves. If we pick here, consider x and y are normed vector spaces, so we can evaluate norms of each vector x mapped to t of x. So basically norm of x means the length of this vector. So if we take the image of x, which means tx, and we calculate the norm of tx with respect to the origin, which means basically length of this vector, these two lengths are equal. That implies this function t is an isometry. So here t is an isometry. So here our t is going from H, which means Hilbert space, to its dual space. Dual space contains all the bounded linear functions. So we call the norm as operator norm, and this space has a norm induced by an inner product. So again, we take any generic term G in H, generic vector, and simply we take the norm of this T of G image. By the definition, it's equal to this one, L of G, LG, sorry, and this simply equal to G. We can prove this part by Cauchy-Schwarz inequality, and finding and by proving this is bounded, we can show this L of G is less than or equal to 1 times G, and we can find a non-zero vector which the equality holds. So when the equality holds, we basically said the operator norm of L of G is equal to the norm of vector itself. So thus T is isometric. Hence, we conclude T is bijective linear isometry from H to its dual space H star. So we found a functional from Hilbert space to its dual space, which is bijective, linear, and isometry. Then we can conclude H and H star is isometrically isomorphic, which simply means this has the same structure. So if we are to work on H star under the over the scalar field real numbers, here this is very important. This is very important because if we pick complex numbers here, if the underlying scalar field is a complex number field, then the linearity fails, because here we get alpha 1 bar and alpha 2 bar. Therefore this function is complex, conjugate linear, not linear. So the linearity fails, therefore we can't find such a map which if the underlying scalar field is complex numbers. So the important part is H and H star are isometrically isomorphic if the scalar field is underlying scalar field is real numbers.